Hi folks, and welcome back to Physics with Captain Rod. I'm making this video to try to demonstrate how to apply momentum concepts to kind of a relatively simple impact example. So in this example, imagine we've got this mass right here, this 10 kilogram mass moving right at 5 meters per second. So the VR1, that's my way of saying, velocity, red mass, picture 1. That velocity is to the right. Imagine at the same time we've got a 5 kilogram mass right here on a collision course moving at 3 meters per second to the left. Now for the rest of this example, we are going to assume that when they impact, they stick together. And maybe there's some Velcro or something on the front of these things. And we're going to then look at or try to calculate the resulting velocity, and then we're going to take a look at the kinetic energies kind of before and after. So when analyzing an impact, you always start by drawing a picture of the system before impact, which I already have drawn. And you put velocity vectors in, right? And those are already given here. So the next step is you draw what you believe the system looks like after the impact. So this is my before picture, and I'm going to kind of put this over on the right. After, we've got the red guy here, blue guy stuck together, entire system moving to the right with some speed which we don't know. I'm going to call velocity 2. Now, sometimes it's not really clear what direction, what's going to be moving in what direction, but taking a look at this, we have a 10 kilogram mass, 5 meters per second. That means we have 50 units of momentum to the right. Over here, we have a 5 kilogram mass, 3 meters per second. We have 15 kilogram meter per second, or 15 units of momentum to the left. So that's the motivation here. The net momentum of the system is to the right. So if they stick together, they will definitely move to the right. So I'm going to kind of separate these pictures here. So to the left here is what I'm calling picture 1, and then to the right, picture 2. Now, momentum conservation can be applied to this because the really important thing is when these things contact one another, there's going to be like a little 50th or 100th of a second where both of these masses are changing velocity. During that time frame, when they're together, if I kind of draw a quick photo, right, the force exerted by mass B onto mass R here, the red one, is this way. At the same instant, the force exerted by the red mass onto the blue mass is this way. The key concept about momentum is this. As long as we consider this our system, both at the same time, the net force on the system is 0, and therefore the momentum will be conserved. So the equation we can write here is this. Conservation of momentum. I usually tell the direction I'm talking about. This is just a 1D problem, but right now I'm referring to the x direction. And then I can write an equation that's going to look like this. Mass, the red mass, m sub r times VR1 plus, I'll go ahead and put a, oh, whoops, that's not a 0. The previous example I did was a 0. Plus the momentum of the blue mass. Now I said plus, but this velocity vector points left, so the momentum is negative, so we're going to have minus mass B times VB1. And then over on the right here, the momentum of the system, well, the mass is the sum of the two times the velocity I called V2. And again, the equals is because of the discussion I had before. As long as we consider both at the same time, the net force during impact is 0, no change in momentum for the system. So if we go ahead and put numbers into this, and I'm going to put a little NCU for note consistent units. So this thing is going to be a mass 10 kilograms, VR1, 5 meters per second, minus 5 kilograms times 3 meters per second equals the sum of the two masses, let's see, would be 15 kilogram times V2. And we go through and solve this for V2. I'm going to write this up here. I get about 2.3 meters per second. So the system should end up moving to the right at 2.3 meters per second. Now I'm also going to take a look at the kinetic energies here for this problem. So momentum is mass times velocity, and kinetic energy is 1/2 mv squared. So basically what that means, or one thing that it means, is that when you have a momentum, you can calculate a kinetic energy that goes with that momentum. So, for example, this momentum term right here has a kinetic energy that goes with it equal to 1/2 times 10 times 5 squared. This kinetic energy would be 1/2 times 5 times 3 squared. The total kinetic energy is the sum of the two. All right, over on here on the right, this momentum has a kinetic energy that goes with it of 1/2 times 15 times 2.3 squared. Again, sticking with my NCU here, my note consistent units. So if we go through and calculate the kinetic energy of the system here, I get 125 joules for this term, 22.5 joules for this term. Again, the total is the sum of the two. And the final kinetic energy over here came out to be, I get around, right around 39.7 joules. Now, one thing you'll notice is this. One of the most common mistakes I see with first semester physics students is this inherent desire to want to put equals between these kinetic energies. And if you watch my previous video, I talk about that, and I'll be talking about it more. Usually kinetic energies are not equal. In fact, in this example, when you take the final kinetic energy and subtract the initial kinetic energy, which is the sum of these two things, we end up with a loss of about minus 108 joules. So what that means is this system dropped in kinetic energy by about 108 joules, and that was just the nature of the impact. In order for these things to stick together, there had to be some material crunched up a little bit or deformed. So anyway, this is how you apply momentum. You draw a picture of the system before the impact and after the impact. You put in relevant velocity vectors. You write a momentum equation, or you write an equation for the total momentum of a system before the impact. You write another equation for the momentum of the system after the impact, taking plus and minus signs into account by direction, because momentum is a vector quantity. Then you just solve for whatever it is you're looking for. Typically, if you look at the kinetic energy before and the kinetic energy after, what you'll find is that the kinetic energy after is almost always less than before. It doesn't have to be. There are examples where it's equal. And there's actually, there are problems where the final kinetic energy can be higher. An example would be if during the impact one of these were spring-loaded or something. Sometimes these little plastic cars we have little springs in them that are kind of compressed. If that spring became uncompressed right during the impact time, you can have a KE final that's higher than the KE initial. But again, those are fairly odd examples. The majority of the time, the final kinetic energy will be less than the initial kinetic energy. So, I hope this video helped demonstrate how to apply these concepts. Have a great day.